What we're going to be doing in this section is using the fundamental trig identities, some of them which we already know and some of them we're going to be seeing for the first time in this lesson, to rewrite complicated trig functions using identities into one trig function. Now, you know some of these identities already. Identities are essentially like math facts, like 1 = 1 is an identity. We know that cosecant of theta is 1 over sine theta. Sine theta is 1 over cosecant of theta. So we have all of these what are called reciprocal identities, which we talked about before. We also have our quotient identities. Tangent of theta is sine over cosine, which means cotangent is cosine over sine. These are all on your formula chart. We've discussed these before, but some of the new identities, these are on the back of your formula chart, are called the Pythagorean identities. They're called the Pythagorean identities because they are variations of a squared plus b squared equal to c squared, which means the way we manipulate the Pythagorean theorem is the way we're going to manipulate these equations so that we can solve for different values. The reason that, again, that this is the same is because cosine squared theta plus sine squared theta is equal to 1 squared, which is 1. So it truly is Pythagorean's theorem with sine, cosine, tangent, secant, cotangent, and cosecant in it. So one of the things I want you to notice, a couple things, cosine squared of theta is not the same as cosine of theta squared. This is saying you're squaring the angle. This is saying you're squaring cosine. Please make sure you use the correct notation where you're talking about squaring the cosine function, not squaring the theta. Like, I will not count this correct. Those are two completely different things. Second thing I want you to think about is maybe looking at just this first one, because you can repeat this idea for the other ones. I wanted you to take that first Pythagorean identity and solve it. Instead of setting it equal to 1, solve it for sine squared of theta. Well, that's very easy. The same way you would solve Pythagorean theorem for b squared, which is to subtract a squared from both sides, you can resolve this equation to sine squared theta. This is also an identity. 1 minus cosine squared of theta is sine squared of theta. If I asked you to solve that equation to isolate cosine squared of theta, again, the same way you'd isolate a by subtracting b squared, you can subtract sine squared of theta to isolate the cosine squared theta. Being able to manipulate these equations, like solve them for different letters, air quotes, different trig functions, is going to be super important for reducing these identities or simplifying using identities and later on proving these identities. So we have a couple examples here. They're already worked out, so you can kind of look through them. If we have sine theta times cosine theta, cotangent theta, we want to reduce this into a single trig function. Notice that cotangent of theta has a reciprocal, that should say quotient identity, has a quotient identity that cotangent theta is cosine theta over sine theta. Okay, so we can use that quotient identity to rewrite it. And then we notice that sine of theta over sine of theta is going to cancel out. So we just have cosine theta left. And I'm done. If we have the second example, cosecant squared theta times 1 minus cosine squared theta, you can do many different things. Like, there's not exactly one way to do this because you can do the math in various ways, which is why your work is so important in this. I'm looking at your work and maybe your explanations for each step instead of just what you're doing on your paper. You have to show work for every question. 1 minus cosine squared of theta using the Pythagorean identity we just solved. That's actually sine squared theta. Okay, cool. So nothing cancels. I don't have 1 left. I can keep going. And remember that cosecant squared theta has a reciprocal identity that cosecant is 1 over sine. So cosecant squared theta is 1 over sine squared theta. But then these sine squared thetas are going to cancel, and so I'm left with 1. We're using these identities to simplify these expressions. We have another couple examples here. Just some more creative ways to simplify these. Sometimes you're going to have to multiply and or work backwards and factor. So we'll go ahead and multiply this one. The reason I can't use one of my Pythagorean identities here. Number one, because there's not one that combines cosecant and sine. And number two, the Pythagorean identities need to be squared. So if you don't have any squares, you're probably not going to use a Pythagorean identity. So my brain thinks, okay, I've got a number or a function in front of these parentheses, I can go ahead and distribute. And so I get this line. And then working creatively, I realize that cosecant of x is the reciprocal of sine. So if I just use that reciprocal identity, the signs are going to cancel. So then I'm left with 1 minus sine squared of of x. Oh, look, that squared should help me realize that, oh, I've got a Pythagorean identity here. This is just cosine squared of x. The last example here is actually a difference of two squares example. And if you notice that this is the difference of two things that are perfect squares, because 1 squared is 1, then you would know how to multiply this without having to show me this work. But if you don't remember that, then okay. So again, I have nothing that I can reduce this with just yet, so I'm going to go ahead and try multiplying. This is sine squared theta, negative sine theta, negative 1. The sine thetas are going to cancel, which gives me, again, this is difference of two squares. Hopefully you see that shortcut. And then this is the Pythagorean identity, but I actually want to zoom in for a second on this Pythagorean identity. Remember, normally we have the identity that says cosine squared theta plus sine squared theta is equal to 1. Well, I want it to kind of match this equation here, sine squared theta minus 1. So if I need that to happen, that means I need this to say sine squared theta minus 1. And then to isolate that sine squared theta minus 1, I'm going to subtract cosine squared theta from both sides. And thus, I have the Pythagorean identity that sine squared theta minus 1 is equal to negative cosine squared of theta. So these problems, you're going to have to work creatively using the identities, the reciprocal, the Pythagorean, and the quotient identities to try to get from the beginning to the end of these problems. There's not one particular way you can do this, and in fact, some of these problems can be worked a completely separate way from what I've done using the same identities, which is just cool.